Welcome back to our statistics learning session. Today, we'll be talking about level, test statistics, and rejection region. Let me draw a graph. Let me draw a graph such that we can see what we are talking about. It will be much clearer if I draw a graph. That's why I'm drawing a graph here. H1, where test statistics is equal to 1. This is probability of showing you the positive hypothesis. Now what we are doing here is that we are drawing a regression polynomial regression line that ends at 1, and we have this boundary k, which is mu, which is 30 for one of the cases which we discussed earlier. Here it should be something like this. Type 2, this point is decided by this k divides the data into two sets. One is theta naught and one is theta 1. Theta 1 are all those points that contributes to alternative hypothesis, and theta naught are all those points that contribute to null hypothesis. We are looking at all those theta 1 that contributes to that that contributes to maximum we are looking at all those points. We are looking at one point that contributes to maximum probability of type 2 error, which is this point. Type 2 max. What is type 2 max? Type 2 max is misdiscovery. We are looking at a type 2 max, even though they belong to theta 1, we are saying that this is misdiscovery. Even though it is theta 1, we are saying that it is actually a theta naught, or it is giving me the test as 1 0. Type 2, even though the point belongs to theta 1, it is giving me the maximum. It is the maximum probability of missing a discovery. In the same way, let's look at all the thetas that belong to theta naught, and we are looking at those points that have max probability of giving 1. We are looking at even though they should actually point to even though they should give you the negative test is true. even though it should give you negative test, but they are giving you the positive test, and we are looking at those points as the maximum probability of that, maximum probability of giving you the positive test, even though they should give you negative test. Therefore, this this is this is this point is power, and here it is same as, it is equal to alpha, alpha equal to power, alpha equal to power. In this case, alpha is equal to power, because same point will give you the maximum probability of two things. One, it gives you the maximum probability of giving you the same point gives you the maximum probability of giving you positive test, while same point also gives you maximum probability of negative test. And I believe these points these points are really close together, even though they're not maximum point. Two points, they are very close together, one belonging to the Sierra knot and another belonging to Sierra 1, very close together. They are very close together, very close, and they lie here. This is what's happening. There are two points that are very close together. One belonging to Sierra knot and one with Sierra 1, and they are very close together. One has a maximum probability of giving you the type 1 error, and another has a maximum probability of giving you type 2 error, and they are very close together, and they are very close together in this continuous line. This is a continuous line. This is a continuous line. This is not a discrete line. It's a continuous line. Even though these point two differences, they are very close together. One has a maximum probability of giving you the type 1 error, that is misdiscovery. Type 1 error, which is a false discovery. Type 1 error alpha, which is a false discovery. One point that has a probability of giving you false discovery, while other point has a probability of giving you maximum type 2 error, which is misdiscovery. And since they are very close together, they will give you about same level. They are those both probability are almost same. Misdiscovery. So we have these 2 points very close to each other, almost they are same, and they are giving you these two information here. Now that is clear. Therefore, we have the type 1 probability. It is controlled by alpha. That means the ceiling is alpha, and you cannot go beyond that. And we are controlling alpha, saying that, as its analogy, we are saying that we cannot we cannot go more than 5%. Alpha can be anything here. Alpha can be either 1%, 2%, 5%, 10%, as you wish. But it's usually a small number. But what we are saying is that the probability of false discovery should not be more than alpha. That's what we are saying. We are putting a stick on the ground and we are drawing a line in the sand and saying that probability of doing false discovery should not be more than 5%. That's what we are saying here. Can we set type 1 error to 0%? Yes, we can. And can we do type 2% error to 0%? Yes, we can. How do you do that? We can do type 1 error to 0%, type 1 error, which is false discovery, by not rejecting anything. We won't reject anything, then we won't have any false discovery. And how do we set type 2 error to 0%? We reject everything. That means we reject all the evidence. Whenever we do the test, we reject all the time, and then there won't be any misdiscovery. That's how we set type 2 error to 0%. Those two are not ideal cases. Those two are not practical. Therefore, we have to get a consensus somewhere. We have to get a consensus at some point, and we have to make some trade-off, and we have to make some cutoff, and that is a critical point here. Second thing is that there is an asymmetry between null hypothesis and alternate hypothesis, and this asymmetry comes from the fact that at any time when we create tests, we are controlling for only one type of error, that is type 1 error, and for type 2 error, we are crossing our fingers really hard, and we are praying for God that that error will not be too much. That's why there is asymmetry between null hypothesis and alternate hypothesis. Null hypothesis is related to type 1 error, while alternate hypothesis is related to type 2 error. Null hypothesis is related to error not, error 1, which is related to type 1 error, and error not is related to type 2 error. Those are two different errors here. We need to understand. Next, we are saying that %. What is 5% here? 5% here is that if you want the maximum alpha or maximum false discovery to be 5%, then we can say that, okay, we'll reject everything. Then we'll be always less than 5%. Isn't that right? To avoid such cases, we need to make this inequality here to be equal. And how do you do that? We do that by creating a test at asymptotic level such that when we have infinite samples, the alpha is equal to actually alpha, not less than that. Else, you can say that if you have certain, if you want to be less than 5%, then you can say that I reject all the I reject I won't reject anything. I won't reject anything. Then you won't have any false discovery, and it's always less than alpha. We don't want that. That's why in as a we can do mathematically, which is very hard. Therefore, in asymptotic, because using asymptotic level, because of Gaussian, since this test is in Gaussian format, we can use asymptotic level alpha such that alpha of test is equal to alpha in when this goes to infinity. That's what we can say here. Therefore, what I'm writing here is when the number of data points is infinite, then this goes to alpha. Next step, the tests usually have the indicator form, and a test is usually a normalized version. Tn is a some normalized version of xn bar. Tn is a normalized version of some xn bar, and it has to be greater than some critical value. There's some flexibility here, and using that information, we are deriving some indicator function, which we call a test and test statistics. And Tn is larger than C. That's our actual test function is. Isn't that right? Yes, it is. And Tn is some test statistics. Tn is for some test statistics Tn. This is not a Tn is some statistics. It is derived by using some xn bar and threshold, some critical value C, and that's how we derive a test based upon some statistics, and this is called test statistics. We could write that we could write this. This is not a universal language. Test statistic can be written other way too. For example, someone can write indicator function with absolute value of Tn greater than C. It's possible also, and there are other forms too. You can say that test equal to absolute value of Tn less than C. These form of test statistics are also possible. Therefore, there's no hard line that there's no hard and fast rule that this is the way to write test statistics. There are many ways to write test statistics. Just to let you know at this point, the main important thing is the form of is a rejection region. And the rejection region is what is the rejection region here? Can you tell me? Rejection region is all the region in a sample space where Tn is greater than C. That's the rejection region. Tn, which is based upon some xn bar, and all the points, when you calculate all the points that have this xn bar is equal to greater than C, that is a rejection region, which will produce us H1, which will give us H1, which is discovery. That's the main important thing you know here. Let me quickly summarize what we discussed today. We discussed about level alpha, and level alpha is equal to alpha asymptotic and asymptotically when n is goes to infinity. Second thing, test is always as an indicator which is made of some function, that is Tn is greater than C. Tn is some normalized form of xn bar. And lastly, test can be many forms, but resistance region always remains constant. And what is the resistance region? Resistance region are those data sets that have Tn greater than C. That's all for today. I will see you next learning session. Thank you so much.